right, so let's start. So last talk for today, and it's a pleasure to have Amol Aggarwal with talk about Arctic circles.
Yeah, thank you very much for the introduction and the invitation to this wonderful program. So let me just start by reminding everyone about six-vertex models and ice models. So we'll start with some domain lambda, which is a subset of Z2. It's finite, and we'll assign to each vertex in lambda one of the following 6 possible edge configurations, 6 arrow configurations. So we have some number of arrows entering and exiting each vertex. Over here, you have no arrows entering, no arrows exiting. Here you have 2 arrows entering, 2 arrows exiting. And each of these 4, you have 1 arrow entering and 1 arrow exiting. The 6-vertex rule is that the same number of arrows come in as go out. Okay, so domain wall boundary condition defined by taking your domain lambda to be an n by n square and stipulating that all arrows enter through the left boundaries, through all sides of the left boundary, and exit through all sides of the right boundary. Now, usually what one does in the 6-vertex model is one assigns weights to each of these 6 vertices. For the purposes of this talk, I'll just assign them to all be 1, but actually everything I'll say, I'll mention a few specific slides in what follows, but all of what I'll say will apply for more general weights, in particular when the delta parameter, this anisotropy parameter for the 6-vertex model is the most a half. Yeah, so, but just for the purposes of concreteness, let me just assume that all the weights are equal to 1. Okay, so now you can view 6-vertex ensembles as collections of non-crossing directed upright paths. So I'll take my paths to be that they can touch, but they can't sort of cross each other. So for example, the bottommost path looks like this. The next path looks like this, etc. So you keep on going like that. Okay. Okay. So what we'll be interested in looking at is the so-called frozen region, which has been, or the Arctic region of the Arctic boundary of these ice models, which have been mentioned to a great extent over the past week. So let me just quickly, so that we're all on the same page, so that we have exactly the same definition in mind, let me quickly say what that is precisely and pedantically. So we'll start with the 6-vertex model E on this domain lambda. So we'll call a vertex V in the frozen region the following holds. So if one of the following holds, there are going to be 4 possibilities. So the first is that every vertex northwest of V is packed. So by packed, I mean it has 2 arrows entering and 2 arrows exiting. Either that, or every vertex northeast of V is vertical, so it looks like this. Or every vertex southwest of V is horizontal, so it looks like this. Or every vertex southeast of V is empty, so it looks like this. So I mean, so if either one of these 4 conditions hold, we say that V is in the so-called frozen region of E. And the boundary of the frozen region, I mean, we will extend only so far. And the boundary of this frozen region is what we'll call the Arctic boundary. And our goal is to basically be able to compute this Arctic boundary for a very large, but when the mesh size or the size of the domain gets fairly big. So as a quick example, you can convince yourself that the bottommost path of a domain wall 6-vertex model, so this green one I've shown over here, traces the southeast boundary of the frozen region. So of course, every vertex southeast of any vertex on this path is going to be empty. Okay. 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 So let me kind of first give you the answer, which I'll first give you sort of the answer for what the Arctic boundary is parameterized as. So it's going to be a union of 4 pieces of an ellipse. So we'll call this A southeast equal to the part of this ellipse, explicit ellipse here. So it's 2x minus 1 squared plus 2y minus 1 squared minus 4 times 1 minus x times y is equal to 1. So this is some ellipse, and then I intersect it with this little box, this 1/2 by 1/2 box over here. Okay, so this gives me some portion of an ellipse I'll call A southeast, and then I do all possible reflections of it. So I reflect it into this line that gives me this southwest, A southwest. I reflect it into the center of the square, that gives me A northwest, and I reflect it into this horizontal line, that gives me A northeast. So I have now 4 pieces of an ellipse. I take their union and I get something that I call A, and this A will eventually be will parameterize the Arctic boundary. And you can see that A is actually not smooth. At its 4 tangency locations, So its derivative, one of its derivatives will be discontinuous. So this is different from what one observes in dimers, where you have completely analytic Arctic boundaries. Here, it's not going to be smooth. Okay, so I'll state a theorem that was predicted that was predicted well before this work. So we'll start with an integer n, which is large, and we'll pick some sample of the ice model, so just a uniformly random sample of the Six-Vertex model with all weights equal to 1 with domain-wall boundary conditions. Okay, we'll let ij be some vertex, so it will be some point in my lattice. And we'll set z equal to the normalization of ij. So I'm just scaling it down by a factor of n. And we'll fix some integer epsilon, which is kind of telling me whether I'm inside or outside this ellipse. Okay, and I'm going to assume that I'm not actually on the Arctic bound, on this A that I described before. I'm not on this union of 4 ellipses. I'm either inside or I'm outside. So I'm going to, more specifically, the distance between z and this A as at most some epsilon, which I can tune to be whatever I want. Okay, so the theorem is that there exists some delta, which depends on epsilon. So with probability at least 1 minus e to the minus delta n, this vertex ij is in the frozen region of M if and only if z is outside the Arctic boundary. So the Arctic boundary only exists, so the frozen region only exists outside of this limiting curve A. And if my z is inside, A and it satisfies this condition that the distance between z and A is epsilon, then with this very high exponential probability, I'm not in the frozen region. Okay, so a bit of history is that so a series of works back at the turn of the millennium predicted that there should exist some Arctic boundary for the Six-Vertex model based on the original realization of this phenomenon and the work of Jakush, Prop, and Shor in 1995 in the context of domino tilings of the Aztec diamond. The question of actually being able to predict what the curve was an open question until Coloma and Bronco gave an answer for this question. So they predicted the explicit form of the Arctic boundary given by this A, the union of 4 ellipses. And through this remarkable work, Coloma and Spartiello reproduced this prediction through what they'll call the tangent method, which I'll talk about more in this talk. And this tangent method turned out, as we've seen in the past week, it turned out to be extremely versatile, producing Arctic boundaries of various classes of statistical mechanical models since this original work. Some of those works, some of these sorts of extensions that use the tangent method to predict other Arctic boundaries are listed, although there are many more which I have not listed here. Okay. So I can rephrase this. I mean, it will be convenient to rephrase this theorem in terms of the bottommost path, which is so more specifically, I'll do the following. So I'll pick some Six-Vertex ensemble E that's sampled according to the S model. I'll denote the non-crossing paths. So I have this family of paths by P1, P2, all the way to Pn. So the bottommost path is P1, the second bottommost path is P2, etc. Okay, and then I'll define this sort of trajectory, this sort of continuum trajectory, this is frac P, by given as follows. So I take I'll go back to the figure in a second. So I take sort of the bottom half of the square, the bottom side of the square and the left half of it. I follow A southeast, and then I kind of go up after that. So it's actually just easier for me to describe in terms of the square. So I1 is just this interval here. This A southeast is here. And then I2 is this thing, okay? So P is just the union of all of them. And the theorem is, the theorem can more or less be reformulated as follows. I can say that the distance between the actual, after I scale everything down by n, the distance between the bottommost path and this limiting trajectory P is at most epsilon with probability 1 minus delta n for any epsilon. Okay, and by symmetry, basically, this is enough. Once you have this sort of southeast part of the Arctic boundary, by reflections, etc., you can get the other pieces of it. So it suffices to basically show the following theorem. So now the proof is going to actually be based on sort of a rigorous the tangent method of Coloma and Spartiello rigorous. And as I'll try to explain to you in the coming slides, this proof is not very model dependent. I just took ice as an example, but it will apply to many other families of statistical mechanical systems. And I'll actually try to point you exactly to the slide where the ice condition is used. And I'll actually, that condition already applies to, that slide already applies to a number of other models. Okay. So Yeah, okay. Something this. Okay, so let me start by just recalling then how the tangent method works exactly. If nothing else, then just to set up notation, which will be useful in actually making it rigorous. Okay, so we have we'll start with some domain wall 6-vertex ensemble E, and it has these paths P1, P2 all the way to Pn and a 7 here. We'll let theta denote the place where the bottommost path exits the bottommost row. Okay, so this theta here is 3, for example. This partition function Zn is counting the number of 6-vertex ensembles on this on the square, and I'll say that the refined partition function Zn of k counts those that have theta equal to k. So I'm counting those whose bottommost path exits at a specified location k. Again, I'll define the k refined correlation function as the quotient of Znk divided by Zn, which you can view as the probability that theta is that the bottommost path exits at the site k. Okay, so the basic integrable into the so exactly solvable input required to run the tangent method is as an asymptotic for the refined partition function, or equivalently the refined correlation function. Okay, so for the ICE model, so you need this if you're going to run the tangent method. I think you basically need some sort of asymptotic of this for the model that you analyze. And for the ICE model, we can okay, so this is, you can kind of check this off with the ICE model, because 25 years ago, Zalberger actually literally just exactly computed what this refined partition function is as a sort of a product of binomial coefficients. And just by applying this with Stirling, Stirling's approximation, you can just compute the asymptotics of this refined correlation function. It's given by exponential of n minus n times some explicit function h of kappa, where kappa is the theta. So theta you should be viewing as scaling like n, so it's kappa times n. And then the statement is that as n tends to infinity, hn of kappa n is going to be exponential of minus n to some explicit function h of kappa, which is defined over here. Okay, I just wrote down the formula just to tell you that it's explicit, although you don't necessarily care. I'm not really going to be using this. I'm not going to be doing any sort of computations for this talk. So, but once you have an explicit h of kappa, you can actually do computations with it. Okay, so now the tangency point you should view as the place where kappa, the value of kappa that maximizes this h of n, which is in particular the minimizer of h of kappa. So just by taking the derivative of this, I can locate the minimizer of this h of kappa, which is where kappa is equal to a half. So the most likely location of kappa is a half, which tells me that most likely we'll have theta equal to n over 2, which in particular is indicating that if the Arctic boundary exists, then the location where it exits the bottommost line, so the location where it's sort of tangent to the domain of the model, is going to be at n over 2, 0. But the remarkable fact is that you can actually use this function h of kappa to not only locate the bottommost point of the Arctic curve, but the whole curve itself. Okay, so let me take a few slides to explain that. Okay, so what we'll do is we'll sort of augment the domain of the 6-vertex model by adding one additional path that starts at 0 minus psi for some parameter psi. Okay, so this gives me, so let's consider some new 6-vertex ensemble on this slightly larger domain with this one new path entering at this location 0 minus psi, and we'll denote the paths on this ensemble again from bottom to top by P1 aug, P2 aug, all the way to Pn plus 1 aug, where this aug stands for augmented. Okay, and we'll let theta denote the location where the bottommost path exits this row here, the x-axis. So theta here is 5. Okay, so the basic belief running sort of that underlies the tangent method is this sort of tangency assumption, which I'll try to explain in this slide. So let's have this capital psi scaling like n. So we'll let psi scale like little psi of n for some parameter, for some real parameter little psi, and we'll select a psi augmented domain, psi uniformly at random. So I just pick one uniformly at random. Okay, so with high probability, the belief is that first of all, this theta will scale like n, so it will scale like theta, like little theta times n for some real number little theta, which will depend on psi. And now the belief is that this augmented curve, the bottommost curve here, which is this brown one, it will first approximate a line ellipsi tangent to the Arctic boundary, and then it will merge with it. Okay. So that's basically the belief that kind of underlies the tangent method and will eventually allow you to compute the Arctic boundary. Okay, so let's take this for granted for the moment and then see how to get the Arctic boundary from it. So now what I have right now is for any point psi, I have a line that's tangent to the Arctic boundary. So in principle, by varying psi, I can get the convex envelope of the Arctic boundary. But the thing is that to determine a line, I need 2 points, not just one. So I have 1 point, which is 0 minus psi. So in particular, if I'm able to determine this theta here, then I managed to pin down this ellipse psi, which in particular pins down the line, which pins down a line tangent to the Arctic boundary for any given psi. And by varying psi, I get the full Arctic boundary. Okay. Now that leads me to the question of how to actually compute this theta. And that goes back to the refined partition function from before. So the computation is actually fairly basic. First, I count the number of paths 0 minus psi to some candidate, some spot here, theta comma 0. So that's just given by I guess theta here I'm denoting by phi. Phi plus psi minus 1 choose phi is just a binomial coefficient, the number of walks from here to here. And then after that, I can kind of erase all of this stuff below the x-axis. And what I'm left with is literally just a domain wall Six-Vertex ensemble whose bottommost path is conditioned to exit the bottommost row at this location phi of theta, which is exactly the refined partition function on hn plus 1 of phi. Okay, so now we plug in. So first of all, I can compute the large n asymptotics of this binomial coefficient, again, just by Stirling's formula. It's given by this sort of entropy function g. And then I also know from before the integrable input is I know what the asymptotics of hn of phi are, and that's given by this h over here. So by summing the sort of blue part and this red part, this gives me some new function which I'm defining by g psi of phi. So it depends on, first of all, the location psi where this brown path is entering, and it depends on the location where I'm guessing the brown path exits the x-axis. So this gives me some function g psi of phi, and just by maximizing this function, I've found the most likely possible location of theta, which in particular tells me where the theta is going to be. It allows me to solve for theta, which gives me the full line. Okay, so to sort of summarize, the tangent method kind of proceeds as follows. So I first get the integrable input is some sort of exact asymptotic or some limiting asymptotic for this refined partition function, which is scaling like exponential of minus n times some h of kappa. Okay, I define this function g of psi by taking sort of the entropy of a random walk plus this, or minus this h that I found up here. I find the maximizer of this g. I let L of psi denote the line connecting sort of this 0 minus psi to this, this should be theta comma 0 instead of 0 comma theta. And then the Arctic boundary is the convex envelope formed by varying all these psi's. So this gives me a very specific sort of recipe for computing the Arctic boundary. Okay, so in terms of mathematics, in terms of making this rigorous, there are a few things that one has to be somewhat careful about, or what I have to really think about. The first is justifying the tangency assumption, but maybe even worse than that is that the tangency assumption assumes that this brown curve is tangent to the Arctic boundary, but a priori it's not even clear that the Arctic boundary exists, namely that that this curve has a limiting trajectory at all. Okay, now even if you assume that the Arctic boundary exists, I've added a new probe, so to speak, and it's sort of this brown path to it, and presumably, in principle, this brown curve could mess up the Arctic boundary. It could shift it. So what you need to show is that this Arctic boundary does not change the limiting trajectory of the original Arctic boundary. Okay, so in the remainder of this talk, I will try to explain. I'll try to sort of outline a route of how to make this tangent method rigorous. Okay, so there will be sort of 3 steps involved. The first is going to be making sense of this tangency assumption. So, sorry. Okay. But in order to do that, in order to explain this, I'll actually need a little bit of notation. So we'll let E denote domain wall 6-vertex ensemble on an n by n grid, and we'll fix some parameter psi, which is some integer, and we'll let E sub psi denote a uniformly random psi augmented ensemble, which is just a domain wall 6-vertex ensemble with one new path entering at 0 minus psi and exiting at n plus 1 comma n. We'll let L of psi, which depends on psi, and it actually is random, it depends on the ensemble. It will denote the true sort of tangent line to the second curve of this augmented ensemble. So I'm letting the second curve of this augmented ensemble be this green curve here, which is P sub 2 aug. And we'll just look at the actual line from 0 minus psi that's tangent to this P2 aug. So in practice, what that means is that you start by making this dotted line, just a horizontal line through P2 through this 0 minus psi. So it looks like this, and then you keep on rotating it until it first hits the green line, the green. Okay, so this will give you some line, which I'm calling L sub psi, and we'll let this omega comma 0 denote the location where L psi meets the x-axis. Okay, and we'll further let theta comma 0 denote the location where P1 aug, sort of the brown line in this augmented 6-vertex ensemble, exits from the x-axis. Okay, so the tangency statement is in the sense that theta is equal to omega, right? Okay, so now to go ahead with proving the tangent method, we'll proceed in 3 steps. So the first is the sort of is a verification of this tangency hypothesis, which is that theta is close to omega. So the probability that theta minus omega is less than some epsilon n is exponentially high. Okay, the second is a sort of concentration estimate, which tells me that this theta n, the location where this actual sort of augmented, the brown curve exits the x-axis, is basically deterministic. It concentrates around some sort of fixed theta of n, which is exactly the, sorry, is there something wrong with this cursor somehow? Okay, yeah. Sometimes when it goes back, okay, that's fine. Okay. This state is again the maximizer of this function. So the second statement is a sort of concentration bound, which tells me that with high probability, this capital theta, which is where the brown curve is exiting the x-axis, constitutes around theta n with very high probability. And the third statement is a comparison. It tells me that this red curve, the P1, which is the true guy I'm after, is close to this P2 aug. So in principle, this brown curve is really just probing P2, this green curve. But I want the red curve to be close to the green curve. Okay, so I will just try to go as far as I can, basically, before time runs out, and making these steps rigorous. Okay, so I'll try to get through 1 at least, and there's a chance that I might not be able to get through 2. So I'll just quickly mention a few words on 2, on the chance that I don't have time to go through it. 2 will kind of proceed in as follows. So what you'll do is you'll couple E and E psi in 2 ways. The first way puts P1 below P2, and the second one puts P2 above this P2 aug, this green curve, above the second curve in this ensemble. Okay, so I'm basically going to kind of sandwich P2 aug, this green curve, between the red curve and the curve right above it. Okay, so then once you do that, the next thing you want to show is that in the actual original domain wall vertex model, that this red curve is close to the curve above it, which is basically, since the green curve is sandwiched between them, that tells you that the green curve is close to the red curve. Okay, so so that's kind of how step 3 will work. If I have more time, I'll go into it. Actually, step 3 is kind of the most technical aspect of it. But what I'll try to focus on for now is sort of the first 2 points. And actually, the second point is basically rigorous already. It follows in a sense from exact enumeration. The probability that theta is equal to some given number phi is exactly equal to the partition, 1 over some. It's proportional, is exactly proportional to the number of paths between 0 minus psi and theta comma 0 times this refined partition function. This is an exact statement. Therefore, once you have any access to h of 8 to this refined partition function, you can basically compute theta more or less exactly. So the second statement is basically exact. It's not where the difficulty lies. So I'll try to make sense of one, and if I have time, I'll also try to make sense of three. Okay, yeah. Okay, so to do this, I'll actually need a little bit of notation. So I'll need a little bit of notation on boundary conditions. So we'll let X and Y denote or if they're either vertices or paths with such that X is northwest of Y. So in terms of vertices, hopefully you know what that means. It just literally means that the vertex is northwest. The vertex X is northwest of the vertex Y. In terms of paths, what that means is that every vertex on X is northwest of corresponding vertex on Y. We'll say that X is less than or equal to Y. So now we have some, we'll say we have some rectangle lambda, and we'll have some sort of barrier paths that are such that all of our 6 vertex paths lie between them. So these are these orange paths here, which I'll call F and G. Okay, we'll let the entrance vertices for our 6 vertex model be U1, U2 all the way up to UM, and we'll let the exit vertices be V1, V2 all the way up to VM. So U1 and U2 are here, and V1 and V2 are here. Okay, and we'll let E sub FG, UW, and super UW be the set of all 6 vertex ensembles on lambda, whose paths are all between the barriers F and G, and such that the entrance points of these paths are V1, V2 all the way to Vn, and the exit paths are the entrance vertices are U1, U2 all the way to UM, and the exit vertices are V1, V2 all the way to Vm. Okay, so this is just labeling boundary conditions. Okay. Okay, so what will be important in the arguments are monotone coupling. So these are sorts of ways of coupling 2 6 vertex ensembles in such a way that one lies above or below the other. Okay, so we'll assume that our boundary data. So let's assume that our boundary data has the following property. So F is greater than or equal to F is greater than or equal to F prime. G is greater than or equal to G prime. U is greater than or equal to U prime, and B is greater than or equal to U prime. And I remind you that greater than or equal to simply means, I guess, southeast of. Okay, so all of the entrance, all of sort of the boundary conditions of this model are southeast of the corresponding boundary conditions in this model. Okay. Okay, so now I'm going to uniformly sample 2 configurations, 2 6 vertex configurations, E and E prime, with this sort of boundary data. So E has boundary conditions given by F, G, U, and V, and E prime has boundary conditions given by F prime, G prime, U prime, and B prime. Okay, I'll denote the paths of these 2 ensembles by P1, P2 all the way to PM, and P1 prime, P2 prime all the way to PM prime. Okay, and the statement that will be used over and over again is this coupling statement. So by a coupling, I mean I can sample both of these random ensembles on the same probability space, such that the following holds. Such that all of the paths, every PI is southwest of every PI prime. Okay, so basically what I'm saying is that if the boundary data of this ensemble is always southwest of the boundary data of this ensemble, then I can couple the paths so that each path in this ensemble is southeast of the corresponding path in this ensemble. Okay, this is a highly intuitive statement, hopefully. Okay, so first of all, you allow to take F prime, G, and G prime to be infinity or minus infinity, which is kind of pushing the boundary data off this way or off this way, so I can kind of thereby allowing me to ignore the boundary condition. The proof is based on it's actually a kind of dynamical proof, which I guess I'll try to explain in the next slide. That was used also by Carwin and Hammond in 2014, although it's a fairly standard trick. And this is really actually the only place where the ice weights are used. Okay, this coupling, it's a fairly ubiquitous phenomenon in the context of statistical mechanics. It's sometimes known as an FKG type condition, and it's not special to the ice model actually. For example, it's known to hold for the 6 vertex model whenever the delta is almost a half. Okay, it also holds for dimer models. It would hold for Philippe's, for example, his triangular ice model. So this is a very general condition, this FKG condition. Okay, so now let me quickly try to explain. This is a heavy slide, so I'll go through it somewhat quickly. How one proves this coupling statement. Okay, so if you ever actually sampled, done a computer simulation of the 6 vertex ensemble, hopefully this argument will actually be fairly intuitive for you. So the first statement what we'll do is there are actually, so what I want is to say that a random 6-vertex ensemble on lambda is southeast of a random 6-vertex ensemble with the new boundary conditions. So, but what I can always do is I can find one ensemble with the original boundary condition that's always southeast of the sort of new boundary conditions. Sort of I can always find one element E0 and E whose paths are always southwest of one element in E prime. Okay, so I can always sort of initialize such that my coupling statement is true. And what now I'll do is I'll run some sort of Markov chain that preserves this ordering, and that eventually will sort of equilibrate. It will tend to the stationary measure. Okay, so what you do is you select a face in our square uniformly at random, and with probability of half, I'll perform an upflip. So I'll kind of flip. If my path looks like this, I'll flip it to this. If possible, in F, I'll do this sort of upflip if possible. So I'll change like a one corner. I'll just flip it to look like this, if possible. And otherwise, with the complementary probability, if I get tails, for example, I'll do the other flip. I'll flip them down. I'll flip it down. Okay. So this produces a new family of sort of coupled 6-vertex ensembles, E0 and E1. And I just keep on doing this. Okay, I keep on doing this I'll keep on doing this. If you've sampled the 6-vertex ensemble, the 6-vertex model on a computer, presumably this is really what you're doing in one sense or another. Okay, so the key point is that this preserves monotonicity. So namely, if all paths in this model are southeast of all paths in this model, then after I apply this flip move, it will continue to be the case. Okay, so I keep on running this model. This dynamic, and eventually it will converge to the equilibrium. So it will converge to the stationary or the uniform state, okay? Which in particular implies that I've coupled the two systems. So since they originally satisfied this monotonicity property, this will produce a coupling between them that will satisfy the monotonicity at the stationary state, at the uniform state. Okay. So this is a fairly general argument, actually. Okay. Okay. So now, so how does one use this to run the outline I was mentioning before? So I'll need a few more or less trivial linearity estimates of random walks. So these are just telling you that random walks are linear, okay? So we'll take two vertices U and V with V northeast of U, so such as here. We'll let the distance between U and V be M, okay? And we'll let L denote the line through U and V, okay? So, okay, so these are just standard linearity estimates. A random walk conditioned to start at U and end at V. It's gonna be basically linear. So what I've written that as here is the probability that that this random walk, this random path P, the probability that its distance from L is at most epsilon L is exponentially high. I need a slight variant of this statement, which is that if I restrict my path to lie below the diagonal, the same statement holds. So if I I take a uniform random path from U to V, conditioned to lie weakly below or above this line L, it's again going to be almost linear. So with high probability, it's going to just basically approximate a line. And if you like 2, but you don't like 1, I should mention that 2 can actually be kind of formally deduced from 1 together with that monotonicity statement. So actually 2 is you kind of almost get it for free from 1. Okay, so now I want to convince you now that this theta, which is where the brown path exits the x-axis, is approximately equal to this omega, where the actual tangent line is close to meets the x-axis. Okay, so let's set U equal to this starting location for the brown path, the 0 minus psi. It's the first vertex in this P1 aug, the bottommost augmented path. And we'll let W, which is up here, it's going to denote the bottom. It's going to denote sort of the first vertex above, or maybe I should say, yeah. So the first or the last vertex, I guess, above the x-axis. That's below L. Okay, so so eventually this brown path, since it exits the boundary, it will touch L at some point. So I'm just finding the point W that's just before it reaches L, which is above the x-axis. So I'm just calling that W. Okay, so I'm now going to condition on a bunch of stuff. So I'm going to condition on all of the black paths here. So all of the P2. I'm going to condition on all of the black paths, so P3 aug, P4 aug, etc. And I'm also going to condition on the green path. And furthermore, I'm going to condition on everything above W. So I'm going to condition on all the fact on the brown path above W. So the only randomness left is this sort of the random walk model, so the random path from U to W, okay, and I'm conditioned on everything else. Okay, so the Gibbs property, the sort of Gibbs property for the Six-Vertex model, what it tells me is that the law of this P1 og, so just this brown path, conditioned on all that stuff, is simply a uniformly random walk, conditioned to start at U and at W and lie below the green path. Okay, so I mean, so yeah, this is just a statement about what it means to condition more or less in this Six-Vertex model. Okay. Okay, so now how does that help us? Okay, so so I'm going to now use the monotonicity to kind of bound this theta above and below. Okay, so to bound this theta below, what I can do by right. So I'm going to let Q be a uniformly random path that starts at U and ends at W and doesn't have any kind of boundary conditions. This is just a free random walk. Okay, so that's this blue curve over here. It's just a free random walk condition to start at U and end at W. And remember that random walks are just basically linear. So by the linearity estimate, I have that Q is basically linear. It's, you know, up to some error epsilon n, it's linear with some very high probability. Okay. Okay, so that means that if Q exits the x-axis at some point gamma, then gamma is very close to this omega. Okay, with very high probability. Okay, so gamma is very close to omega, just because I mean the full blue path is close to the full L line, so that means that the places where they meet the x-axis are going to basically be the same. Okay, so now the point now is that I can use monotonicity at this point. See, the brown path is a random path conditioned to start at U and end at W and lie below the green curve. So now that means that by monotonicity, the green curve is only pushing the brown curve down. Okay, so if I remove the green curve, then the brown curve goes up in a sense. So more formally, what that means is that I can couple the brown and the blue curve so that the brown curve always lies below the blue curve. Okay, so more specifically, maybe the boundary data, as you can see, the boundary data for this model is all southwest of the boundary data for this model. And in fact, there's no boundary data for this model, but there's only, so that means that the boundary data can only push the brown curves down. So by monotonicity, that means I can couple P1 og, the brown curve, and the Q, so that P1 og is always southwest of this Q. In particular, what that means is that the exit point, this theta, is always bigger than the gamma. Okay, so with high probability, that tells me that theta is larger than equal to gamma, which by the fact that gamma is close to omega tells me that with high probability, theta is up to maybe some epsilon fudge. It's very close to this omega. Okay, so that could be one bound of this statement. Okay, so now I need the other bound. I need to show that theta is maybe not so far to the right of this omega. Okay, so what I'll do instead, I mean, what I did last time was I kind of pushed this green boundary off to minus infinity. I kind of pushed it off to as northwest as it can be. So to get the other bound, what I'll kind of do is I'll push it as far down as it can be, which basically means I'll push it down to this line L. Okay. So more specifically, we'll consider this orange boundary path here, which is just tracing the line L, and we'll let R be a uniformly random path from U to V that's conditioned to lie weakly below L of psi. So okay, so again, so then this is just a random walk conditioned to start at some point, end at some point, and lie below the diagonal. So again, by the linearity estimate, what I know is that R is basically linear with very high probability. So in particular, if R exits the x-axis at some point, upsilon say, then upsilon is again very close to the omega. Okay, yeah. Okay. So now again, by monotonicity, this I'm kind of pushing the green path down to the dotted line. So that tells me that I can only push theta forward. I can only push the brown path down or sort of southeast. So by monotonicity, I can then couple the blue and the brown paths so that the brown path is southeast of the blue path. Okay. So in particular, what that means is that theta is at most going to be upsilon. Okay. So so in particular, the probability. So now, as I said before, upsilon is basically omega. Upsilon is at most omega plus epsilon n. So in particular, what that means is that theta is at most omega plus epsilon n with some very high probability. So there are any sort of questions so far with this? Okay. So how much time do I have left?
Like 5 minutes.
Okay. Sorry.
5 minutes plus.
Okay. Okay, so now I want to tell you about the next step of the argument, which what I've done so far is I've explained why the sort of the tangency assumption holds. The next part I want to explain is why the addition of the new path doesn't change the Arctic boundary by very much. Okay, so as I mentioned before, if I go back a little bit, I said this kind of proceeded in 2 steps. The first step was to couple E and each psi in 2 ways. The first way was so that this P2 og lies above P1, and the second way was so that this P2 og lies below P2. So that kind of sandwiches the green between the bottom 2 curves in the E ensemble. And the second step was to show that these 2 bottom curves in the E ensemble are close. So if I sandwich it between 2 things that are very close, that tells me that it's close to any of them, right? Okay, so I want to maybe explain a little bit about these 2 points. Okay, so right, so I've restated my goals over here. So first, to couple to implement the coupling in 2 ways, and the second is to show that the paths these P1 and P2 are close. Okay, so the first step is actually a direct consequence of monotonicity, actually. So as you can see, so let me first try to explain why P2 can be coupled with why P2 kind of lies below the second curve here. Okay, and the reason is the following. I can view this topmost path. So there are n+1 paths here, and there are n paths here. Okay, so first observe that the bottom n paths here have boundary conditions that dominate, that are southeast of those in this ensemble. And it also has one additional path that can be viewed as a barrier, this kind of short little top left path. So by monotonicity, that tells me that I have the boundary data of each side dominates the boundary data of E, which tells me that all the paths in each side dominate those in E, which in particular tells me that the second path, the green path in each side, dominates the second path in this one. Okay, so that immediately tells me that these 2 can be coupled in such a way that P2, this one over here, is northwest of P2 og. Okay, now the second coupling, the reverse inequality almost, is the following. So I view the bottommost path I view this brown path as a barrier. Okay, so I view this as kind of a barrier. Now the boundary data for the rest of the paths here are equal to the boundary data for the rest of the paths here. So this brown path can only push this green path up, right? So that tells me that this green path is kind of above the red path. So this P2 should be a P1. So this green path lies above. It can be coupled. These 2 models can be coupled in the way so that this green path lies above the red path. So this gives me 2 couplings. The first is that so that the green path lies above the red path, and the second is that the green path lies below the second curve in this E ensemble. Okay, so my last step is then to find a way to show that these 2 curves are close, that the P1 and the P2 in my original model. In fact, you can see that since I've done the sandwiching, I can ignore this augmented ensemble and only look at my original ensemble E, so that the bottommost and the second bottommost curves in this ensemble are very close to each other. Okay, so I'll just quickly sketch it and then I'll stop. So, right. So to remind you, my goal is to show that the distance between these P1 and the P2 in my domain, my original domain wall Six-Vertex model are close. And the step the argument kind of proceeds in 2 pieces. The first is to show that these P1 and P2 are almost convex. And the second is to show that the approximate convexity of P2 implies that that P1 and P2 are close to each other. So let me just kind of give you a picture that will hopefully convince you of the latter statement. So let's suppose that I knew that P1 and P2 were approximately convex. Okay, so now let's suppose that I'm on this terrible event in which P2 is actually very far from P1, and I want to show you that something bad happens on the event that will make it very unlikely. Okay, so here I've kind of drawn a picture of that. I've drawn P1 as these piecewise linear things. I've drawn their convex hulls, which are these dotted lines. And if you grant that P1 and P2 are approximately convex, what that's telling you is that P1 and P2 are basically equal to their convex hulls, these dotted curves. Okay, so now let's suppose I have some point V2 on P2 that's very far from the corresponding point V1 on P1. Okay, so what I'm going to do is I'm going to kind of draw a line through V2 that's perpendicular to the line connecting V1 and V2 as shown over here. So now if now P1 is kind of a random path. Okay, so this dotted line here, it will intersect P1 at some points U and V, say. Okay, and now P1 is basically conditioned on everything else. P1 is going to be a random walk starting from U and ending at V that's conditioned to lie below P2. Okay, so now as I was mentioning before, such paths are basically linear, which tells me that the trajectory of P1 on this dashed line had better be very, very close to linear, which in particular tells me that V1 had better be very close to this dashed line, which in particular says that V1 is very close to V2. So this is some way of showing that these two paths are very close to each other. So that was somewhat sketchy, and I apologize for that. So maybe I'll just conclude. So we established some Arctic boundaries for the domain S model. It proceeded by justification of this tangent method by Colombo and Sportiello, which involves inserting an augmented path in our domain, which would be tangent to the Arctic boundary, and using the refined partition function as a way of identifying the trajectory of the path. So the integrability is really only used in the computation of this refined partition function, and you don't really need the full exact solvability of the model to pull this off. And the proof of argument basically proceeded through an analysis of non-intersecting paths ensembles that is reminiscent of these sorts of line ensemble techniques used by Corwin and Hammond. And to show the tangency hypothesis, we really only use sort of this Gibbs property and the monotonicity. And to show that the fact that the new path doesn't really affect the Arctic boundary, we kind of showed some convexity hypothesis combined with monotonicity and the Gibbs property. So thank you for your attention.
All right, questions?
Yeah, you mentioned that some estimates are hold not only for ice point, but also for delta less than 1/2, I believe, right?
Yeah.
So can you explain?
So the only point where I'm using delta, actually, everything I said is going to be correct for general ice. Random walks are going to be linear in sort of an ice environment. All that's going to be fine. The only place where I used the fact that I'm dealing with ice is the slide that I'm not being allowed to go to. It's this slide over here, this monotone coupling. The fact that if the boundary data of one model if I push down the boundary data, then I'm pushing down the interior paths. Okay, this is also known to be true for text almost a half. And the same argument, the sort of Glauber dynamic argument, will apply to the proof will work exactly the same. Yeah. Now, if delta is bigger than a half, then what can happen is that in this Glauber dynamic, this monotone preserving property will be false. So local moves. Well, what can happen is that when I try to do this flip, if I imagine that my value of A is too big, then maybe this A will kind of be stuck to the path above it, and it will kind of refuse to flip. So that's what goes wrong when delta is bigger than a half. But if delta is less than or equal to a half, then this argument will prove the monotonicity, and then the rest of the argument just goes through exactly the same way. Yeah.
All right. Anyone else? Okay.
Among the questions that you have raised at the beginning, there was the question of the very existence of the Arctic curve.
Yes.
So I'm not sure to have understood at which point of the arguments you.
Just at the end.
Ah.
Yeah. I mean, you kind of get the Arctic curve by applying the tangent method. It's only attained at the end.
I see.
Yeah, because what you get is a series of bounding curves that bound it. And yeah, so what you'll get is a series of you'll get all possible tangent, you'll foliate all possible tangent lines that will give you every possible point at the Arctic boundary. And that will tell you in particular if the Arctic boundary exists. But other than that, I don't know of a direct way to show the Arctic boundary exists. Sorry? Yeah, so I mean, right. So what this will buy you, sort of what the first step will buy you. So okay, right. I have these three steps, right? And you're asking which step would you actually pin down the Arctic boundary, right? Okay, so the third step, sorry, the first step will tell you that kind of P2 all this green curve has that you'll more or less get from the first and I guess the second step, but that tells you nothing about the red curve. So you really need this third step to conclude that the Arctic boundary exists. Yeah. Did I answer your question? Yeah.
So actually, I wanted to ask exactly the same question. Like you proved that P1 is tangent to P2.
Sorry?
What you showed is that P1 is tangent to P2.
Yeah, that's right.
Yeah, but is there any other way to characterize the circle? For example, the measure at the north, northeast is different than the measure at the southwest.
Sorry?
Is there another way to characterize the Arctic Circle?
Oh, other than the convex envelope, or
yeah, for example, the measure northeast is different than of the vertex.
I'm not sure if I understand. So I mean,
so below is frozen and above there is some other measure.
Yeah, but what you can kind of symmetry, what you can kind of do is you can rotate the model and you can reduce to the like yeah. So you, as you said, there are actually 4 pieces of the Arctic. There are 4 pieces of the Arctic boundary, which are these 4 pieces. And this, I've only pinned down these pieces, but the others just follow by symmetry. I don't know of sort of a more direct way of getting these pieces other than to kind of rotate them to make this region kind of empty, and then apply the tangent method there. Actually, this Philippe Di Francesco in his talk on triangle ice kind of faced a similar issue for one of his models, and actually that kind of prevented him from seeing the full Arctic boundary in his case. Yeah, for certain boundary conditions, he faced this kind of issue that symmetry did not suffice symmetry did not suffice to make this region empty. And for that reason, he mentioned in his talk that he actually was not able to pin down what the Arctic boundary was there. So this seems to be necessary to kind of rotate the domain and use some sort of symmetry to make one region empty, and then apply the Arctic boundary there, the tangent method there. Yeah.
All right. No urgent question. Okay, let's thanks Amol again.